Dear colleagues, welcome, welcome to Australia. My name is Alexei Kondurin. I would like to tell our results on curing of composite materials in free space and what can be done with this technology. So this talk is about what can we do in future. What about our space exploration? Really space exploration, deep space, and so on. So. This is our future. This is not completely futuristic talk. This is not fantasy because we have in hand some materials which can be used for creation of large space structures. So let's start.
Our space flights were started almost 70 years ago. It was a tiny one-pilot cabin turning around the Earth. It was perfect at that time. It was enough volume to survive in space environment for a few hours or days if you are a hero. Another kind of space construction is a space station. This is first Salyut station, launched to its orbit in 1970. It was more than 50 years ago. The station has a larger volume than a spaceship. Humans can work here for a few months or years if they are heroes. Salyut station is one block. It was made on Earth and launched as ready-to-use construction with all pre-installed equipment. Modern International Space Station consisted of some blocks made in ready-to-use state on Earth and launched to space. The blocks are joined together in orbit. It required multiple launches, own engines at each block, or external orbital carrier in orbit. It required a complicated procedure of docking. These blocks and equipment must be strong enough to survive at launch acceleration. The mass and size of each block are limited by launch carrier. It took 10 years to assemble International Space Station in orbit. Overall, it costed 150 billions in price of 2009. Total pressurized volume is about 900 cubic meters. Can we build larger station? It seems not. There is a fundamental problem. We are limited by rocket ability to deliver a payload to orbit. We can deliver maximum 20 tons to low Earth orbit today, or maybe 150 tons in future. This is not much, not a principal difference. With present technology, we cannot make larger station. We cannot build large interplanet spaceship with all systems required for a long space journey. We cannot place really large scientific or industrial equipment in orbit. We cannot build greenhouse to provide sufficient food for astronauts. We cannot provide sufficient radiation protection for the crew. We cannot make spaceship with artificial gravity. All these structures require much larger pressurized volume in space construction. We are restricted to low Earth orbit. We need permanent delivery from Earth. We are short-term tourists in space. We are not settled in space. For real space exploration, we need to be free in space, independent in space. We need significantly larger and heavier constructions in space. Finally, we need O'Neill torus, big enough to put plants, animals, humans in artificial Earth. Then we can fly to other planets and stars. So we have to rethink all our space programs, put this goal and achieve it. And then we can really to be settled in space. How real is it? How far is a future of the large space construction? Let's look at tendency of pressurized volume or space construction with time in our history. The tendency follows exponential law. It means the large space construction of some thousand cubic meters is not far away from today. How can we get it? I propose a principally new way, making in space, building in space, the same as we do it on Earth. When we need big building on Earth, we build it in right spot. We do not move big building in ready to use conditions from factory. We build it where we need it. We have to do it in space too. We can do it with the curing of composite materials directly in space environment. We work with this concept many years. Composite materials are the same materials as we use when we fly with airplane. Prepreg as a fabric with uncured resin is prepared on Earth, packed compactly into container, delivered to orbit, unpack and unfold. Then the resin is cured directly in free space. Finally, we get large, strong construction in orbit, or on Moon or Mars. Then the construction can be pressurized with air, and crew can install all required systems: thermal protection, radiation protection, power equipment, life support system, space garden, and so on. We propose a wall consisting of prepreg with liquid resin that will be cured in free space environment. The prepreg is open to free space environment. It solves a problem with residual gas during the inflatable process, but it makes a problem of liquid components in vacuum. The hermetic shell provides a hermeticity of the construction. The top rear layer provides required temperature range of the wall and prevents sticking of the wet resin layers. The thickness of the wall can be 5-10 millimeters independent on strength requirement. Free space is not friendly environment for liquid resin. The free space environment is characterized by high vacuum, space plasma factors such as low energy atomic oxygen flux in low Earth orbit, high energy particles, and different radiations from the sun and deep space. Temperature variations between minus 150 and plus 150 and microgravity. These conditions are destructive for any kind of materials, including composite materials. These are very unusual and harsh conditions for the curing process of composites. Because the curing reaction in composite materials is sensitive to the environmental conditions, we carried out a large number of experimental investigations of curing reaction in simulated free space environment, such as high vacuum, plasma chambers, and temperature variations, and in stratospheric flights. We have shown that there are some compositions of epoxy resins and hardeners which can be successfully cured in free space conditions, and they can give sufficient mechanical strength of the composite cured in orbit. These results were presented and published in many ways. If somebody is interested in details, please ask me. What can we build with such composites cured in orbit? We optimize the size of construction which can be transported by modern space carriers to Earth orbit on the one side, and the composite wall which provides sufficient strength of the construction on the other side. For example, the ordinary existing cargo space carrier, like for example Falcon 9, can deliver a container of about 20-21 tons with uncured prepreg to its orbit, where the prepreg can be unfolded up to 100 meters length and 10 meters diameter and cured. After complete curing in orbit, the construction can be pressurized with air. The pressurized volume of such construction will be about 8,300 cubic meters. This is after one launch, one rocket with 20 tons payload. Compared with total volume of International Space Station, now about 900 cubic meters, after 10 years of multiple space launches. This is a big difference. Such a big pressurized construction can be used for a large number crew. Have a look at on previous stations for small crew, with the same specific volume per crew member as for International Space Station. The crew in big station can be increased up to maybe 60 members or more. This is big difference for scientific activity at the station, for industrial activity. Can be used even for touristic activity as space hotel and many other applications. Using heavier space carrier, which can deliver, for example, 150 tons to Earth orbit, a large space construction can be delivered, unfolded and cured in space. For example, modern heavy carriers such as SLS or Heavy Falcon or Starship can deliver such heavy shell to its orbit, shell of a cured prepreg, that if the shell will be cured, it can give construction of 200 meters length and 18 meters diameter. The pressurized volume of such construction would be 53,000 cubic meters. And for these constructions, I used parameters of not the strongest composite. The composite is used for these calculations has a strength of about half of gigapascal. This is not the best. So possible to find much more better composites on the market. What can be done with them? The strongest composite with tensile strength of 1.5 gigapascal can be used for really large space construction. For example, the spherical construction of 66 meters diameter and mass of 150 tons is viewed as the maximal pressurized volume which can be achieved with modern composite materials and modern space carriers. The pressurized volume of such construction can be 150,000 cubic meters. The curing in orbit is unusual and complicated process. It must be monitored during the flight because the curing reaction is sensitive to temperature and space radiation. The temperature of the construction wall must be monitored. The space plasma environment with different energy and kind of particles must be also monitored. Distribution of curing reaction completeness over the construction wall surface must be monitored. The number of embedded sensors together with robotic scanner moving on the construction surface could be useful. The analysis of the curing completeness and prediction of the composite strength must be done before the construction can be evaluated for usage. After the construction is evaluated, the cargo and crew spaceships can be docked to the docking unit. The construction can be pressurized with air and crew can install all required systems. External thermoregulating isolation, thermoregulating systems inside, radiation protection system, power system, and other systems. The station can be equipped with large area solar panels. These panels can be done with the same curing technology in orbit. The large station, of course, would require much more power than a modern International Space Station. The radiation protection can be significantly improved with using of water as the best material for radiation protection. Calculations show that 30 centimeters of water would be sufficient for solar and galaxy radiation in space journey outside the radiation belts. For really strong protection, the water cans, altogether 3 meters thickness, can provide sufficient radiation protection, better than on Earth or on International Space Station now. Such radiation would be sufficient for intergalactic journey for unlimited time. The water layer around the construction can be used for a water-based life support system. For example, chlorella plants for air regeneration human waste regeneration, water plants, animals for food, and so on can be used. Different kinds of internal structures corresponding to the flight aims can be installed later by crew. For example, cross-section walls, along-sector walls, cylinder walls, and other structures. In particular, the cylindrical structures can be installed to maximize the area of space garden. Such construction can be used as a specialized space garden module, providing food in orbit for other missions. If solar panels cannot provide sufficient energy or the spaceflight mission is far from the sun, the atomic power station can be placed on a safety distance from the construction, fixed on frame or with cable. This way for power station can be very important for deep space missions where sun radiation could be low or even neglectable. The construction can be used also to install and adjust self-regulating permanent biological system as life support system with stable development, air, water, and water regeneration as it works on Earth. The construction can be used for installation of artificial gravity system, such rotation system. Such system does need a high speed of rotation, but it can be useful for recovery of the crew members against the microgravity health problems. For example, sleeping in such system would recover the human organism during the space flight. The new kind of scientific stations would be available. The service and scientific parts of crew can be much more efficient as on ISS, where all astronauts fulfill all duties as pilot, repairman, engineers, and scientists together. In large crew, these functions can be split that increase the productivity of scientific work. The scientific crew can be extended up to a number of small research institute or large laboratory on Earth. Sufficient pressurized volume of the construction would permit to install large amount of industrial equipment. Permanent orbital telecommunication station with crew. No more many communication satellites. No more space debris. Serviceable, upgradable station on just a stationary orbit or low orbit. The large construction can be used as a space garage for local spaceships or satellites. For example, the satellite can be placed inside the construction. The construction is pressurized with air, and the crew can repair the satellite as on Earth. A number of large constructions docked together with different functionality can be used for orbital spaceport. Such spaceport in orbit can be as service port for many different space missions. It does need landing or does need support from Earth. The docked together large constructions as space gardens, space garage, crew model, and so on can be used as permanent space shuttle between planets. Local small spaceship can circulate between Earth and shuttle and other planets. And then flight trajectory can be designed in such a way that space shuttle wouldn't need power consumptions at all or minimum to fly between planets. Finally, a combination of curable large space constructions can be used to create a really large spaceship with permanent biological self-regulated life support system, power station, radiation protection for intergalactic journey. All such constructions can be delivered to orbit with modern existing space carriers. For example, the spaceship consisting large livable spheres with external technological modules can be occupied by 1,000 crew members. this number of humans is sufficient for genetic stability of human population. Such intergalactic ship can travel from Earth to other planetary systems forever, hundreds and millions of years. This is a realistic way to spread biological form of life in universe.
So, as you see, we stay at the door of new era of space exploration. We have these composite materials which can be cured in space in hands, and we can use it now. Let's do next step. Let's go for space forever. Let's settle in space. Thank you for your attention.